So, yes, I'm happy to be here. So this is, my instructions was to give like an introduction to localization, which is really an ancient topic. So I felt a bit uncomfortable covering, half a century of research. So I'm going to focus on something which happened in the last 10 years, who knows, something like that, which is really a new development of this old field. Dirac fermions, Majorana fermions. It will be kind of like a basic talk. So even if you're not, these concepts are not particularly informative for you, that's okay. And as it was suggested, please interrupt me for questions. That will be very helpful. I was in La Zouche just last week.
This is, okay, sorry. I just realized that in the program, you have 2 talks.
Yes, I'm also.
And this looks like the second.
No, it's not. It's
okay.
not. It's not. It's not. It's not. The other is localization landscape, which is a very. No, it's not. Don't worry. It's not. It's not. It's not. It's not. It's not. It's not. No, this is an introduction to localization, but somehow in a 21st century package rather than a 20th century package. So please, raise your hand or just shout. No need to raise your hand and ask questions, because otherwise it's not going to be very enjoyable, I'm afraid. So yes, this is an old topic, and let me see if this works. It works. There was even a book. 50 years of Anderson localization. That was 2008, this century, but already 15 years ago. Time flies. So this was 50 years of development studying this partial differential equation, right? Some Laplacian, that's the kinetic energy, some random potential energy, and then you can study it in 1 dimension, you can study it in 2 dimensions, you can study it in 3 dimensions. Who knows, you may even be courageous and study it in higher dimensions. And let's say somehow the discovery of Anderson was that, if this potential would have deep wells, really deep wells and high barriers, then you could imagine that electrons would be trapped in this potential, right? So that's not remarkable at all. If the potential is very rugged, like some mountain, if it's a mountain landscape, then the electrons will be trapped in some valley, and that's, you could call that localization if you want to. But the discovery of Anderson was much less intuitive. Was that even if this potential is very, very shallow, just ripples, and the electron has more than enough kinetic energy to just sail over the potential landscape, it will hardly feel it. Still, if the system is big enough, the wave function will be confined to some, you can see a plot like here, it will be confined to some rather small area. It will not be able to escape from that. When if you would look at the potential landscape, you said, there's no valley there. Why is the electron trapped? Why doesn't it move around? That was the discovery. So that's now called Anderson localization. The weakness of this potential landscape, so that it's very shallow, is measured in this way, that we say there's the mean free path, and there's a wavelength, and we want to have the mean free path much larger than the wavelength. So that is what we call a weak potential. And it can localize electrons, and the mechanism by which it localizes electrons is quantum interference. It's destructive interference, which somehow traps the electron. So this is an old topic, and I'm not saying that it's solved, but it's just a topic in which many people have worked on. And just to show you a bit, get you a bit used to this old topic, just to familiarize you with that. We could even consider just a one-dimensional system. It will also happen if you just have a waveguide or a wire. It doesn't need to be 2D or 3D. And the one-dimensional case is kind of helpful because it's the only case which we can solve exactly. So it's kind of helpful. So this is a plot, just a little computer simulation which I ran, where I have some wire which is disordered, weak disorder, some potential which varies. And I calculate the transmission probability through this wire as a function of energy. This is Fermi energy. That doesn't really matter. Delta is the level spacing. This wire will have a level spacing, right? If you close the wire, there'll be bound states in this wire, and they will have a certain spacing delta. Now I'm opening up the two ends. So the electron which I inject can pass through and escape at the other end. And that's called the transmission probability. So this is some number between 0 and 1. And it depends on the energy. So you can change the energy. And here it says Fermi energy. That's kind of irrelevant here because I only have a single electron. So, and you see this function is very spiky, right? I mean, sometimes it sails through almost with unit probability, but then other times it's very, very small. And this phenomenon that you have these spikes is very familiar in quantum physics, of course. It's what we call a resonance. A resonance. The very simple example, of course, if you have two barriers, then there will be certain energies where you can just sail through these two barriers. And here it's a bit random because I don't have two barriers, I just have this disorder potential. So there are resonances, and you know, typically the spacing of these resonances will be the mean level spacing. If this will be a system of two barriers, then you would, in these two barriers, you would have quasi-bound states. And then whenever you hit a quasi-bound state, you would have a resonance. So the spacing of these resonances will be this level spacing, which in this case, on this axis is 1. And indeed, the average spacing between the peaks is approximately 1 unit. But then there's another energy scale, of course, in this problem. That's the width of the resonance. How broad is it? So this resonance here, for example, is incredibly spiky, very, very narrow. This one is much broader. And so there will be some sort of characteristic resonance width. And the characteristic resonance width in a disordered system has a name. It's called the Thouless energy, for a reason which will become clear in just a moment. And you could calculate the ratio of these things. This will be a dimensionless number. The resonance width over the resonance spacing will be some dimensionless number. And the discovery of Thouless was that this dimensionless number, if you multiply it by a squared over h, gives you the order of magnitude of the conductance of this system. It's an order of magnitude. It's not an exact correspondence. There could be numerical coefficients here. But in order of magnitude, this is what it means. Conductance of a wire is e squared over h times resonance width over resonance spacing. Now you can understand a criterion, which is the Thouless criterion for localization, which is this. So imagine that these resonances, you know, if the resonances overlap, if you have overlapping resonance, you almost form a band, right? Basically, the formation of a band in a metal is due to overlapping resonances. And when they overlap, you just forget about the resonances and you just have a smooth dispersion, a cosine, for example. So if the resonance width is much bigger than the spacing, then you will have a band, which will mean you'll be able to freely propagate through the system. If, however, the resonance width is much smaller than the resonance spacing, then typically for most energies, you will have no transmission. And so that's what we would call localization. And so Anderson's criterion for localization was localization happens when the conductance drops below e squared over h. Now you might say it's kind of obvious, but it certainly wasn't obvious in the 1970s. The whole role of e squared over h as an important quantity was not appreciated at that time. So this was Anderson's criterion. He said once the conductance of a metal drops below e squared over h, then the system becomes localized. Neville Mott then called this the minimum metallic conductivity. That turned out to be a concept which has not withstood the test of times. Basically, it's a crossover effect. It's not really a minimum. It's not that something abruptly happens when G is e squared over h. It's a crossover. If you're much smaller, then the conductance is exponentially small. If it's much bigger, then the conductance just follows Ohm's law, a metal. And from this, you can actually infer another quantity. So if the conductance is exponentially small, you might ask, what is then the localization length? Right? So the wave functions will decay over some length exponentially. It's called the localization length, and also the transmission will then decay exponentially on that length scale. So if you're in the localized regime, the conductance, the transmission probability, will be exponentially small. So it will be like e to the minus. Let me see if I have chalk here. Is there even chalk here? There's a blackboard. There's a blackboard. There could even be chalk. Here, there's chalk. That's chalk. Good. We're not doing too well on questions, by the way. That's not good. But right, so you have something like a conductance or a wave function, which will decay like. So if you have wire of length L, the conductance will decay with this length scale L, measured of the units in some characteristic length. And if you look here at this formula for the conductance, we actually know what is the conductance of a wire. Well, perhaps you don't know, but I know. It's called the Drude formula. It's a textbook formula which says that the conductance of a wire, always E squared over H. So this is, N is the number of modes in this wire. You know, wire, you could think of it like a waveguide. So it will have a certain number of modes. The number of modes is basically the cross-section of the wire divided by the wavelength squared. And then there's a mean free path, and then there's the length of the wire. The fact that the conductance decays as 1 over L is just Ohm's law, right? If you make the wire twice as long, conductance becomes twice as small. And the fact that it's proportional to the number of modes is also kind of a no-brainer, right? If you make the wire twice as thick, probably the conductance will be twice as big. And then there's this mean free path in the numerator. So it's not really rocket science to imagine once the conductance becomes exponentially small, which means that this means that the conductance will become exponentially small when this drops below E squared over H, right? When this drops below A squared over H, it will become exponentially small. And actually, it's just a small step to then deduce that probably this localization length will be this coefficient here. Right? So that when this coefficient is much bigger than unity, then of course the exponential decay is gone. It's only when the coefficient becomes smaller than unity that this becomes important. And we have now theories, we can calculate it even with all prefactors and the whole works, but this was basically Thouless intuition, if you wish, or understanding, that the localization length in the wire is number of modes times mean free path over sample length. This has one far-reaching consequence, because typically we think of motion through a wire as diffusion, right? You diffuse, like a random walk. And so for diffusion, you need mean free path smaller than the length of the wire, right? The mean free path is like the step size of the random walk. So you want to have the wire much longer than the mean free path. But this is it's not possible in 1D. In 1D, there's no diffusion at all. If you have only one mode, strictly 1D system, then N is 1. And so, yes, the localization length is this is a mistake. There should be no, here, it's gone. Localization length, of course, is a length, right? So in a wire, the localization length is just the mean free path. So in a one-dimensional wire, you're localized after one collision, no matter how weak the disorder. That's, of course, a very, very striking result. No matter how weak the disorder, after one collision, you're localized. After two collisions, order of magnitude unity. So there's no diffusive regime. But if you have many modes, if N is a large number, then you could have some big room, right? And typically, think of a metal wire will have N is 10,000 or 100,000. So in a metal wire, there's lots of space to have Ohm's law. But then if you make it longer and longer and longer, at some moment, you're localized. Good. So this is a little bit of intuition where we started in 1958, right? This was 1958. Now we're 1972. We're making some progress. Let's see. 1984. Okay, we're yes, please. By all means. By all means. Absolutely, absolutely.
There is another parameter in the system which is sort of the size of the bulk, right? So you have a piece where the eigenfunction is large and then the rate of decay. What do you know about the size of the piece where the eigenfunction is large? It's not the same.
Well, in these, the type of systems we're studying here, which is just weak disorder, these are parametrically the same numbers. I mean, I'm pretty sure you can come up with unusual disorder. but in these systems, parametrically, these are the same. So the wave function is just like a yes, yes. So all of this is for weak disorder. So all of this will be near the center of the band when KFL. That's the. I mean, the basic assumption in all of basically in pretty much everything which I'll be saying is that KFL is much larger than 1. So the mean free path is much bigger than the wavelength, much bigger. So all these disorder effects are really very weak kicks. That's why you can make everything. You know. I mean, this is maybe somewhat of a disappointment, in particular for the localization landscape fans here in this audience. But for, let's say, for physicists, typically when we worry about localization, we worry only about weak disorder. And certainly Anderson's heroic accomplishment was not to demonstrate that if you have huge peaks in your disorder potential that the electron is localized. That was not his accomplishment. Everybody understood that. His accomplishment was that even if the potential is just a ripple, you know, and you will just sail through it, then you're localized. So all the good stuff, so to say, is KFL much larger than 1. So, you know, very weak disorder. But very large systems, of course, disorder is weak. But so thermodynamic limit is definitely a valid region to think about, but it's always in the limit of very weak disorder. Yes, I think it's also so that is somewhat the bias which at least physicists have in this business. Yes. But actually, 1D, actually in quasi, we call this quasi 1D. When n is bigger than 1, we call it quasi 1D. This is the only instance where everything can be solved exactly in this limit of weak disorder. In the limit of weak disorder, you can solve basically for any question you have has a rigorous answer. But it's good. We had the first question from a professor actually, so that's semi-good. So more. Yeah. Yeah. So more questions. Yes, please. Well, nanowires, I mean, the word nanowire doesn't mean much. It means nanometer, so you have to ask what's the wavelength, right? So if it would be metallic, the wavelength could easily be 1/10 of a nanometer. So you would still have 10 modes. So I would call this quasi 1D. If it's a carbon nanotube, very quickly you'll have just a single mode. We have no difficulty actually in physics to make wires which are single mode, but not in metals. In metals it's pretty much impossible, but in semiconductors. In semiconductors we can have wavelengths which are perhaps 50 nanometers. And so then it's really, so the single mode regime is absolutely accessible. It's not a problem at all, but not in a metal. In a metal you will never be single mode. In a metal basically the wavelength is the atomic separation. And so the wire, yes, it will be a couple of atoms wide. So good. Let's have more questions. That's really good, right? Yes, please.
So in 2D here, is the formula, you don't remove the big L?
No, in 2D, it's. I think I will have the formula in 2D. So 1D, the localization length is this, without the L, right? Number of modes times mean free path. In 2D, it's exponentially large, the localization length. It's exponentially large in mean free path over sample length. There's no number of modes.
So the bigger the sample, the larger
No. Localization length, of course, is a concept independent of sample size. You divide by. So this was a mistake, right? I could even let me correct it right away. I'm gonna hang on. No. There was a mistake, and you're completely right. And I should correct it right away, which I'm going to do.
I'm talking about the other formula.
Yeah, the other. Okay, now I've lost my cursor. Okay, now I'm dead. Please, cursor. Here it is. The cursor. Here's the cursor. Bam. And then we play. Which error did you notice, my son? No. So that's right. So this formula here.
No, just below you wrote it in 2D. It's the 2D formula that he's asking about.
It's there. Yes, it's there. It's.
So here, the bigger the sample size, the bigger the localization.
It's oh my goodness. I mean, okay, this is a talk. To my, let's say, to my excuse, I'll say I made this talk especially for you, right? So it's a new talk which I made. It's the first time I'm giving this talk. It's the first time I'm giving this talk, and there we go. So it's mean free path over wavelength. So in the weak wavelength limit, it's exponentially large. No, so it's the first time I'm giving this talk, and so there may be more typos. It also happens if I teach a class. I could give you bonus for the, but it's good. You have to correct me. That's I like that. Thank you. So we're okay. We're getting in the right spirit to ask questions. That's very important. Yeah. So it's exponentially large in 2D, which is it basically means yes, the states are localized, but it's very difficult to see it. And yes, good. So 1972, let's move on. We're getting there, friends. We won't go very... 1984. So this is the small, you would say, change of the problem. We add a vector potential, right? So instead of just having P was a derivative, right? So the Laplacian was just, if I remove this, I get the Laplacian. I add a vector potential, and that gives me then the effect of a magnetic field. And this is a very neat twist. And the theory of localization, at least the framework of the theory of localization, was developed in the 1980s by my Dutch colleague Aad Pruisken and Dima Khmelnitsky. And they, I could say, postulated, there's no theory here, but there's informed, let's say, informed guesses, if you wish, or meaningful ways to think about this. They formulated this scaling diagram, which says, so once you have a magnetic field, conductance becomes a tensor, right? Becomes a tensor with diagonal and off-diagonal elements. We're still in 2D. In 1D, the effect of the magnetic field is gone, right? In 1D, a magnetic field has no effect. There's nothing to deflect or do anything. So 2D is the simplest case, so and this is indeed the case you want to study. So in 2 dimensions, so you have sigma xx, which is the diagonal element of the tensor, and the off-diagonal element of the tensor, which is here. So this is called the longitudinal conductance. This is called the Hall conductance, transverse conductance. And they conjectured, if you wish, that there's no derivation, but there's lots of experiments which validates this, that if you would, let's say, lower the temperature or increase the system size, do anything which would make your system bigger and more quantum, then your conductance would flow according to these lines. So let's just dwell a moment on what this means. So 1/2 is somehow really special, right? If you're on the 1/2 axis, you see, you would flow to this fixed point here, which would have a longitudinal conductance of some number and a Hall conductance of exactly 1/2, but this will be an unstable fixed point. It's unstable because if you just move a little bit away from it, you would deflect away from it. So the meaningful fixed points are here, 0, 1, 2. Those are the physically meaningful fixed points. And the longitudinal conductance is 0, and the Hall conductance is an integer in units of e² over h. That is the quantum Hall effect. That's, say, the big discovery of Klaus von Klitzing. That's the experiment. The experimental discovery of Klaus von Klitzing, that if you have some system at low temperatures in a magnetic field, 2-dimensional system in a perpendicular magnetic field, its longitudinal conductance will be 0, and the transverse conductance will be quantized in units of e² over h. And yes, please. 2D. 2D, and the magnetic field is in what type? Yeah, I know. Yeah, if it's in plane, it will have no effect. In plane has no effect, so it's a 2D system. It's basically a semiconductor, a two-dimensional semiconductor with a magnetic field perpendicular to it.
And so why is there a difference between? Oh yeah, so it's just okay. So x is just sigma xx, sigma y is the same thing.
Yes, absolutely. Sigma xx, you have a tensor which has 2 diagonal elements which are the same, and the arc diagonals differ by a sign. Yeah. Sigma xy is minus sigma yx. Absolutely. And so this is a neat thing. And actually here you can define at this point here, at this unstable fixed point, you can define a critical exponent, because this unstable fixed point here, so the system is localized pretty much everywhere, right? It's pretty much everywhere sigma xx goes to 0. But at this point here, it doesn't go to 0. At this point here, it floats. It flows to some value here. There's some unit here. I think it's 0.6, some number which is not particularly relevant. It's just some number of order e squared over h. And here, so here it's scale invariant. If you're at this point here, you can make the system bigger and bigger and bigger and bigger. It won't localize. You'll have a certain conductivity, which is some magic number, let's say 0.6. And now you might ask, how quickly will you approach that? Since the system does not localize, it means that its localization length goes to infinity. It will typically go to infinity with some power law. I mean, that's the belief in all this business, that the way in which localization lengths diverge is with a power law. So there will be a localization length psi, which will depend on energy. And it will depend on energy. There will be some characteristic energy. I have no idea what this characteristic energy is. It's some parameter of your system where you reach the fixed point. This is not universal, but the universal thing is believed to be this exponent nu. So the way, as you flow towards this unstable fixed point, the localization length diverges, and it diverges with some exponent which is believed to universal. This EC will depend on material properties. That's not interesting. The interesting thing is this nu. All of this, say, intuition, of course, comes from theory of critical phenomena. Right? In theory of critical phenomena, this is how you analyze critical phenomena, and this is what's called a quantum phase transition. So typically in critical phenomena, your scaling parameter is temperature. You do things as a function of temperature, say water to liquid to gas transition. But these are transitions at 0 temperature, so they're called quantum phase transitions. They're called quantum phase transitions because they're not thermodynamic. They're not thermodynamic. And so you might ask, what's this number nu? You know, this is the type of problem which theoretical physicists like, right? Some universal problem, very well-defined problem here, very well-defined Hamiltonian, very well-defined quantity. I've removed everything which is material specific. So I don't have to talk to experimentalists, ask them how big is your system, you know, what is it made of. I'm talking about, let's say, formal, mathematically inclined theoretical physicists, right? And they will get one number, and this number will be universal, so 100 years from now it will still be with us. And so the amount of energy which has gone into calculating nu is tremendous. I have colleagues who spent their entire career trying to do that. Pruisken is one of them. Martin Zirnbauer is another. And there are more who spent their entire career trying to calculate nu. And they all failed. They all failed. So it's not the type of problem I would like to give you as a PhD student or a postdoc, right? Yes, please. Well, there's no, okay, hang on. So here everything is static here, so I don't have any time dependence here. So this is the only problem. This is the only this is a static thing. This is in this flow diagram here. This is the only exponent which exists. This one here. We know even, you know, let me even make this a bit stronger. You might say, okay, well, perhaps, you know, we don't know it exactly, but we can do numerics and we'll find it very accurately. Even the numerics is not on secure ground. For many decades, it was thought to be, you know, close to 2.2, close to 2. And then better numerics, you need bigger systems, of course, to extract it. Better numerics from more recent dates now somehow convinces us that the exponent is close to 2.6. Experiments measure a value which is much larger for reasons which we do not quite understand. It could be due to electron-electron interactions. We don't quite know. So even if you say, well, I'm not really interested in an exact theory, but even, let's say, on the more qualitative thing, this topic is still not finished. Yes, please. Absolutely.
So here, when you say that you have localization, you assume that in your to connect with understand localization that you have a disordered system with disorder.
Absolutely. Yes. Yes, yes. Without this, everything is, I mean, Anderson, you might say this is not Anderson localization. Anderson himself thought this was the cleanest example of Anderson localization. So, okay, you might say he hadn't thought about this when he wrote his book, paper in 1958, which is true, but it's yes, so you're localized with broken time reversal symmetry. Let's say in the big framework of things, what I did before in the previous slide was localization in the presence of time reversal symmetry. Now I have localization in the absence of time reversal symmetry. And these things matter for critical exponents. This is something which we are very familiar with. It's symmetry classes, dimensionality. It's universal to some extent. If you change something really fundamental in your Hamiltonian, like added symmetry, or change the dimensionality, then critical exponents are allowed to change. But we do believe that within that framework, this number nu, which we now believe to be close to 2.6, should be approximate, should be universal in that sense. So if you solve this problem, your career is guaranteed. I'm not saying, in mathematics you have these problems like, proving Riemann hypothesis, P is NP, where you somehow do this one thing and nobody will ask you, what have you been doing lately, right? So here it's that, right? If you analytically compute this number, you're done. You're done. No, you could make the problem more complicated, of course, but in this particular case, and also the experimentally relevant case, this is just b times x in the y direction. A is b times x in the y direction. The fun thing happens if the magnetic field is completely uniform, nothing happens, and then there's this potential landscape. A is b times x in the y direction. Yes, you could ask what would happen if you also add this order to A, and we believe nothing will change. Yes, that is different. If this is gone and A is disordered, then you're in a different symmetry classes. I'm not going to tell you anything about that symmetry class, but this is a different symmetry class, and you will have different critical exponents, and everything will be different. Yes. So this is definitely the case. If you remove this and you have only disorder in A, that is different. But if you have disordered V, then you could add disorder to A. And I used this word symmetry class already several times now. I will dwell a bit in that for a moment. For now, the only symmetry class I want you to imagine is or keep track of is, do I have time reversal symmetry or not? That is the key thing. Good. We're doing pretty well, and we're getting more questions. So I'm really happy with that. This is perfect. Please keep this up. Okay, 1982. I'm somehow switching the topology. 1984. 1982. Okay, the chronological order is slightly off here, but we're almost done. I think this is the last one of the old topic thing. This is Teiki NN, Thouless, Komoto, Nightingale, and de Nys. De Nys is actually my colleague from Leiden. They somehow generalized the quantum Hall effect to something which is much broader now. They realized that the quantum Hall transition, you could call it an Anderson transition. Yes, it is an Anderson transition. But in the modern language, we would say this is the first of the topological phase transitions. And so this is now, if you open arXiv every single day, just open arXiv ContMat today, probably 20% of the papers will have topological in the title or abstract. This is an obsession, right? Topology. And then if you look at the papers and you read them and say, where's the topology? Somehow, okay, we've become enamored with that word. So we now argue that the quantum Hall transition is a topological phase transition. Topological phase transition means that the thing which changes at this phase transition is not something like a density of states or some other order parameter. It's a topological quantum number. Topological quantum numbers can only change in discrete ways. Typically, they're integers. And what is the topological quantum number in the quantum Hall effect? Well, you might say it's the conductance in units of E squared over h, right? Which it is, right? The thing which changes as you go through transitions in the quantum Hall effect. Think of this thing here, right? It's if I go from this fixed point here to this fixed point to this fixed point, the thing which changes is sigma xy in units of E squared over h. But it's not topological. It doesn't seem to be topological. And so what TKNN showed was that actually it is topological, and there's a way to formulate that. This is actually from a paper from one of my students. It's because it's a bit of a different way, which I like. And let me just briefly show what's the formula. So this is a formula where I have a system, say some conductor, and I look at its reflection coefficient. I have some lead attached to it and I reflect from it. And this system encloses a flux. There's a flux piercing through it. So I have a reflection coefficient matrix. Actually, it's a matrix because I have different modes. I have a reflection matrix which depends on the flux. And now I carry out this operation. I take the log, I take the determinant of the matrix, take the log, take the derivative, and then integrate over phi over one period. And this has to be an integer, and it is in fact an integer. And the integer is a topological quantum number. So this is a different way. This is not the way TKNN wrote it down. They used the language of Chern numbers, which is a bit of a different way to do it. Chern number is for a closed system. This is for an open system. I prefer the open system thing because I like to do conductance. But it's the same thing. The I happens, of course, because this R will go through 0, and when it goes through 0, the logarithm will pick up a phase. This is actually a plot. This is just a computer simulation where we have some system. We have some system where we vary the chemical potential, and then we plot this topological quantum number. And you see the different stripes. These are all different phases and their phase transitions. So this is somehow the modern way to think about the quantum Hall effect. When we think about the quantum Hall effect, let's say and write papers at this time, we say the quantum Hall effect is a topological phase transition. There's a topological quantum number. You might call it a Chern number, or you could give it another way.
What are the coordinates?
Yeah, the coordinates. I have two parameters. I think it's magnetic field on the y-axis and Fermi energy on the x-axis, and I calculate for each of these parameters this particular quantity here. And the colors then tell you in which phase you are. Just to show you that you know you can make complicated phase diagrams if you like, so Chern number, this here I would call it a flux winding number. It's the same thing. There is a topological invariant which is associated with these phase transitions. And you can then ask again questions about how this topological invariant changes. You will have critical exponents. And this, let's say, is the theory of quantum phase transitions from the topological point of view. And again, there's no, all of this is numerics, insightful intuitions. Nothing which would even be the beginning of a theory. We're used to that. I'm used to this. I've been in this business for many years. I'm used to it that we need computers to somehow validate our things, and that there's very little we can do analytically. Good. Yes.
Can you say again what the topology is?
Yes. So so this word topological by physicists is used whenever we have some object which we can calculate, and which, I mean, in a very crude way, I would say is used whenever you have an object which we can calculate, which can take on only discrete values. And in this case, you would say it's the topology of phase space, if you wish. There's a torus, so there's some notion of topology. And the Chern number, you know, or typically one would associate the Chern number with something saying the topology of your phase space. But I'm not able to really now immediately tell you, okay, this is like being a donut or an orange, right? How you would explain topology, like to clueless people, right? So, in fact, in the way I typically like to do these things, which is like here, I would call these things not topological invariants, but algebraic invariants. I'm calculating the determinant. I can calculate a trace. I can calculate a Pfaffian. So the way I encounter these things is more through algebra, linear algebra, rather than through topology. But if you're more sophisticated than me, then you look at this from a different perspective and you say, no, I realize this is Chern number.
So here it's
just a ring.
you get by complex integration.
Yes. So it's totally okay if you just use this word topology as jargon, right? Topology means, in the physics context, it means it has to be universal, material parameters should not enter, and there should be something which will change, not like magnetization, which would be an order parameter. If the magnetization changes, we wouldn't call it topological. If it's some number which changes from one number to another number, we would call it topological. In fact, we even make this distinction. We will then say, will the number vary over all integer numbers? Then we call this a Z topological phase transition. If it can take on only two values, we call this a Z2 topological phase transition. It's all just jargon. It's kind of helpful, and we're used to jargon. We use jargon all the time. And yes, please.
Would not the topology come from the topology of H state?
Yeah, but It could, but these typically will be systems with periodic boundary conditions. I don't have edge states, so you know. But I'm not saying. I mean, I use the word also, but this is what we've become used to. Certainly, you know, when the theory of the quantum Hall effect was developed in the 1980s and 1990, nobody called this a topological phase transition. So this is a new way of looking at it, and it's kind of helpful, and it's okay. Good. So this is basically a sum up of what I've told you now, and we're doing really well on time. So it's an old topic. There's some experiments, not many experiments, but there are experiments. There's lots of numerics, lots and lots and lots and lots and lots of numerics. There's no analytics except for the 1D case, the quasi-1D case. The quasi-1D case is the only case which we can solve exactly. Quasi-1D meaning multi-mode wire. You know, basic questions like what is the expression for the localization length with all the coefficients in there? What is the critical exponent, not just estimated but calculated? There's nothing there. And it's not for lack of trying, right? I mean, really, really high-powered tools have been used for this. Nonlinear sigma model, conformal field theory. It's not just naive people just fooling around a bit. As I say, you know, really very, very powerful mathematical physicists spending their entire career trying to solve this problem, and they have not succeeded. And so that's, we've become used to that. And so this is not the direction where I expect much progress in the 21st century. So what's happened in the 21st century, that instead of, you know, hitting our head against the wall and trying to do this where we haven't succeeded, is we've gone in a different direction and said, you know, let's expand the topic, let's make it richer, expand it, get new phenomenology, do new fun things, instead of just trying to solve unsolvable problems, which is basically the advice I would give any student, right? If you look for a problem, don't look for problems which have not been solved, but try for problems which nobody has tried to solve, right? That's a much smarter way to proceed. And the new phenomenology is, so all of this has been just for ordinary Schrödinger equation, let's say ordinary electrons, right? Basically, Stephen's spin does not really play a role. And the new phenomenology happens if you then look at more exotic particles, which we now call Dirac fermions, Majorana fermions, and they've become really, you know, very trendy in the 21st century. And so how does localization look like for Dirac fermions, meaning relativistic wave equation, Majorana fermions, a real wave equation? How does that work? And so let me first tell you a little bit about Dirac fermions. Of course, this is a bit, again, this is also jargon, but jargon helps, right? It helps us to. This started basically with graphene. In graphene, it was realized that the Hamiltonian of graphene is not p squared, but is linear in p. It's linear in p. Of course, p is a vector, so you contract this p with a matrix. It is still a matrix. So the Hamiltonian is a matrix Hamiltonian. You might think it's a matrix because you have to accommodate spin, which is indeed true. It's just that somehow in graphene, for some technical reason, it's not the real spin. It's something which we call the pseudo spin, but that shouldn't worry us at this moment. So let's just pretend that sigma is the Pauli spin matrix. So I have a spin degree of freedom, and I contract it in this way. I say sigma x is multiplied by px, and sigma y is multiplied by py. And the thing in front is a velocity, but just a c number. It's not an operator. Right, and just to remind you, right? So sigma x, right? These are these Pauli matrices, right? This is just this one, and sigma y is this one, and sigma z is this one. They're also sometimes called sigma 1, sigma 2, sigma 3. They're the spin operators, and so this is. Linear in momentum. V is just a C number, so the velocity is energy independent. The velocity of these particles is not dependent on energy. And then I can add a scalar potential. Of course, since these are 2 by 2 matrices, I have to multiply the scalar potential by a unit matrix, but I didn't write this explicitly. So we call this a relativistic Hamiltonian, which is also a bit of a jargon because, of course, these particles are just in some semiconductor. They're not moving at relativistic speeds. They're certainly not. But the fact that the velocity is energy independent is something we know, for example, for the photon, right? The photon moves at the speed of light, irrespective of its frequency. And so here something similar happens. These electrons move with some velocity v, irrespective of their energy. And so that's why this is sometimes called a relativistic wave equation. And it applies, well, most cleanly it applies to what's called a topological insulator. Topological insulator is some material which is completely insulating. It has no states. It has no states except at the surface. At the surface it has states, and these states are described by this Hamiltonian. That's some sort of magic material. And we just discovered, I mean the community discovered these materials 10 or 15 years ago. And the crazy thing is we never knew that these materials existed until 15 years ago. And now we know that they're ubiquitous. Ubiquitous means they're everywhere. So it's not some rare material, oh my goodness, I found it. No, they're everywhere. Nature is chock full of topological insulators, and we somehow completely overlooked them for a century. So that's kind of crazy. And so this is one of these obsessions. You can basically spend your entire career now exploring topological insulators. So they're these strange materials, they're insulators. Again, there's this word topological, I can't help it, that's the jargon of the field. They're insulating in the bulk, but on the surface they're conducting. And they conduct according to this Hamiltonian. So these are spinful particles, they're just electrons if you wish, but somehow due to the magic of this periodic potential in which they move, in this periodic potential, their Hamiltonian is not p squared, but it's this Hamiltonian here. And then there could be some disorder. Now, if you look at this Hamiltonian, we say that this Hamiltonian has symplectic symmetry. That's a word. It's a type of time reversal symmetry, but it's a special type of time reversal symmetry where you invert the momentum and you invert the spin. You see, I go p to minus p, sigma goes to minus sigma. If I do that, you see that the Hamiltonian doesn't change. Hamiltonian doesn't change. You may have ideas about time reversal symmetry being like complex conjugation of Hamiltonian. For spinless electrons, that's indeed what happens. For spinless electrons, time reversal symmetry just means real Hamiltonian. Here, for spinful electrons, it's a bit more complicated, and we have a different word for it, which is symplectic. So symplectic symmetry is just this p to minus p, sigma to minus sigma should leave H invariant, which it does. Now, the same thing would apply if I would completely replace this thing just by p squared over 2m, right? And perhaps add spin-orbit coupling. So this is not the first time the spin of the electron played a role. For heaven's sake, not. So traditionally, in the 20th century, we would have just ordinary Hamiltonians of the form p squared over 2m. And then we would add what's called spin-orbit coupling. Spin-orbit coupling could be something like px sigma y minus py sigma x. It's called spin-orbit coupling. And then we could add a disorder potential. So these will be massive electrons with spin-orbit coupling. They also have symplectic symmetry, because obviously this first term here, p to minus p, sigma to minus sigma, yes, it's invariant. And there we know very well what happens to localization. So there's this diagram here. This is a similar, I showed you scaling diagrams here, right? Here I had sigma xx versus sigma xy. But now it's somehow easier because I have time reversal symmetry, so there's just one conductance. The conductance is not a tensor. And so I don't have to do this scaling diagram in 2D. I can just have a scaling diagram where I plot the conductance here. This is the conductance. And this is how the conductance changes as I make the system bigger and bigger. Yeah, do it logarithmically for convenience. So if you're on a point on this curve, if it's positive, if this thing is positive, it means that G increases with system size. If G increases with system size, it means you'll flow through the right. If you're negative, then you'll flow through the left. So you see, this is again an unstable fixed point. Right? Here I flow to the right. Here I flow to the left. So this is an unstable fixed point here. It's again a Anderson localization, delocalization transition. And you could ask again, what is the critical exponent here? At this fixed point, at all fixed points, at a fixed point, the conductance is scale invariant, which means that the localization length should diverge. Yes, please.
This is a bit different from, the gang of four.
No, this is the one.
Yeah, but okay.
This is the one.
They have overall increasing. It's the vertical axis.
It's because they don't have. It's because they don't have this term. They don't have this term.
So this, the decrease of the function with g goes to infinity goes be
Absolutely, 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 absolutely.
and it's in 2D.
2D. This is in 2D. 2D with spin-orbit coupling. Actually, I don't think this. Yes, this is in 2D with spin-orbit coupling. Absolutely, 2D with spin-orbit coupling. No, this is special for this. It's not, but this is not new. I mean, even the gang of 4 knew about spin-orbit coupling. This is just ordinary Schrödinger electrons with spin-orbit coupling, and there's this critical point here. And there the conductance is K-invariant. It doesn't flow to the right, it doesn't flow to the left. Yes, it's unstable, still it's K-invariant. So localization length has diverged. And you could ask the question, as I approach this transition, how quickly does it diverge? And there's again a critical exponent. In this case, it's 2.7. You know, before it was 2.6, now it's 2.7. You could say, who cares? Which is true. Mathematical physicists care. But yes, it's all... And again, we have no theory for this, but this is what numerics tells us. It's approximately 2.7. Numerics also tells us that this critical exponent is 1.4 times 2e squared over h. Big deal. The factor 2 here, of course, we now measure conductance in units of 2e squared over h because... oh boy, I lost my cursor. Is it back? Yeah, it's back. You know how this cursor works, right? This is an incredible piece of high tech. Don't you think this is an incredible piece of high tech? It integrates in real time Newton's equations of motion to track the cursor on the screen. It's not a laser pointer, obviously, right? Don't you think it's amazing? Computational power in this thing? I think it's absolutely mind-boggling. But sometimes it crashes and I lose it. So 2e squared over h because of spin, and then the 1.4, big deal, that's some number. Okay, so this is the old stuff, let's say 20th century. Now we go to 21st century. Yes, please. Some random potential. Weak disorder, and everything. As I said again, you know, I'm only interested in weak disorder, weak random potential, short correlation lengths, nothing. And then you can make it more exotic. You could say perhaps it's a fractal. All of this, you know, the problem is complicated enough as it is, right? It's not that then we have to enrich it to make it more fun. No, this is the complicated problem. And so, which is good, that the simplest thing you can possibly think of. So typically we take Gaussian white noise. That's in a computer, that's typically what we take. We just take some Gaussian white noise, and that's a big deal, that's it. Yes?
I'm a little bit confused because the Dirac form of the Hamiltonian near the Dirac points is not related to the spin of the particle. You obtain this because when you develop
It is?
Hamiltonian, because it's a bipartite system.
No, hang on. Okay. So hang on. So you know too much. You know too much. This is why I put this between parentheses, right? So if you know about graphene, it's much more complicated. Let's forget about graphene. So graphene, all of this is way more complicated. There are valleys. The band structure of graphene is much more complicated than this. Historically, indeed, that's how it happened. Dirac fermions first emerged 2005, Geim-Novoselov graphene. But that was how history gave it to us. And this is much more complicated because it has 2 valleys. It has actually 4 degrees of freedom because I also have the valleys. And somehow, so I started out working on graphene in 2005. And then as a gift, as a godsend, in 2008 or 2009 came topological insulators. I could throw away all this baggage of graphene. I could throw it away. In a topological insulator, you have an absolutely clean 2x2 Hamiltonian, real spin, no worry about pseudospin, no worry about intervalley scattering, to hell. And in fact, this is how it was presented. I still remember the very first talk I heard by Laurens Molenkamp. He said, topological insulators, that's the better graphene. It's what graphene should be, but somehow didn't fail to deliver. So, so we can forget about graphene here. That's kind of helpful. But indeed, it also represents one single valley of graphene. So if you're somehow clever and you're able to eliminate intervalley scattering, this is it. Because the spin in graphene is somehow irrelevant, it's a pseudo-spin. But these are all kinds of extra complications which, unless you have a specific interest in carbon monolayers, is good. Yes, please.
Just a general question. Here you're talking about Anderson condition in 2D.
Absolutely.
Very nice appearing with the synthetic symmetrical. But you always mention that you're interested only on weak disorder.
Absolutely. Yes, so 3D and 3D Anderson transition is another layer of complexity. From the topological point of view, there's not much fun. It's very much 20th century physics. I have nothing new to tell you about, and so yes. So all the good new stuff. So it's also an unsolved problem. Nobody's been able to calculate anything. We wouldn't know how to do anything. No, I have nothing. I have nothing creative to say about 3D. 3D Anderson transition. It's a metal insulated transition. We can try to solve it on a computer. It's even complicated to solve it on a computer because it's 3D. So experimentally, it's difficult. So it's certainly difficult to do if you want to do it with classical waves. In fact, with classical waves, it's pretty much impossible. Not impossible, but pretty much impossible. And it's for some, it's kind of like it's a dead field from my perspective. I mean, there's nothing I could possibly do about it. Whereas here, this is new stuff, also because we're so limited that we cannot calculate anything, right? So I need qualitative new stuff to do anything. Of course, if I had a theory for 3D Anderson transition, I'd be here shouting and presenting it to you, right? But I don't. Nobody has. Good. Even this simple, 2D weak disorder, nobody has any theory there. Good. Good. And now we do the same thing, but instead of p squared over 2m, we just remove this thing here, right? We just get rid of this. We just have px sigma x plus py sigma y. The fact that there's a minus sign here, it's all irrelevant. But so now we have just this thing. So here say, right, surface of topological insulator or single valley in graphene. And this is how the scaling function looks like. It's always positive. It's always positive. The transition's gone. It's always positive, and so it doesn't localize. I mean, it will just flow to infinity. In fact, I can even tell you how quickly it will flow to infinity. It will flow to infinity like log L. So the conductance is some coefficient, let's say e squared over h, times log sample size over mean free path. Ha! Yes, nothing, right? So this was this Hamiltonian here, p squared over 2m plus px sigma y minus py sigma x. But I'm just confusing you here. Let's just write px sigma x plus py sigma y. The fact that I had different numbers is irrelevant. Here I had this plus v, of course, right? That's massive electrons with spin orbit coupling. I remove the p squared over 2m. Gone. Yes. It's kind of strange because you say, look, for small momenta, it's a quadratic term, should be irrelevant. I could just get rid of it. It's quadratic, it's higher order. Yes, it's quadratic, it's higher order. You remove it, and you remove the localized phase. This is magic, and this was only discovered. This is a paper from my group, 2007. There was lots of discussion because we didn't know okay, so why do we know this? We cannot derive scaling diagrams like this. Nobody can. So you conjecture them, right? And so there were two schools there. There was one school which said it's this, and the other school which says it goes down here. And we did very extensive computer simulations to show that this is indeed what happens. In the absence of theory, that's what you do. So it doesn't localize at all. And the conductance, in fact, this is kind of crazy, right? Log L over L. It means if you add disorder, you make the mean free path shorter, the conductance goes up. Isn't that crazy? You add disorder, and the conductance goes up. Logarithmically, very slowly, but still it goes up. I still remember the very first time we saw this on a computer. It was a shock. I somehow didn't know this. I didn't know this at all. And we started out with very weak disorder. We added more disorder, and the conductance just went up. Yes, please. Yes, so, okay. putting things on a lattice is a separate talk which I could give to you. Putting things on systems on a lattice, putting Dirac fermions on a lattice is not easy. So, you know, I could give you a seminar on this if you're interested. But, you know, typically, how do we put things on a lattice? We say, well, P is like a derivative, right? P is a derivative, so that is some, say, function of x plus a minus the function of x minus a divided by 2a, right? And perhaps you can do it more cleverly than that, but that will be the first thing. If you do that, you get this thing, the band structure changes in a dramatic way. Because in momentum space, fx plus a minus fx minus a over 2a, in momentum space, it's a sign dispersion. So this band which we had here, let's see, the eraser is here, right? Here it is. I'm not allowed to stand here because of the recording, so I move back. Right? So the first thing which happens if you put this on the lattice is this. There's your nice Dirac point here. This was your Dirac point. You get another Dirac point here. This is pi over a. That's the first thing which happens if you put this on a lattice. And so that's problem number one. Even if the disorder is very weak, you have to somehow get rid of this. This is an industry. It's something which people from particle physics know very well. It's called the fermion doubling problem in that context. Because, you know, they do things like lattice QCD. They always put the relativistic fermions on a lattice. And so they always have to get rid of these doublers. And it's fun. It's neat. You can do that. It's crucial. If you don't do that, if you keep the doublers, the thing will just localize. That's the first thing that happens. And so this is typically what will happen also if your disorder is too strong and the bands do all kinds of strange stuff at higher energies, eventually you'll localize. Eventually you'll localize. Well, there are various. So in a real system, there will be various limitations. The first limitation, indeed, is you have to ignore coupling between the top surface and bottom surface. This will be like coupling between two fermions. So it's on the opposite surface. That's one thing. And then I presume also there's also the gap. I said the surface is insulating, but it's only insulating, of course, to some degree. There's a finite gap. You know, I'm pretty sure that in real life, if I say it will never localize, oh my goodness, there will be limits to this, right? But the mathematical, if you wish, or the physics statement is this particular Hamiltonian does not localize. And then if you say, let's apply it to real systems, then this linear dispersion at some moment will die. And it's not the type of thing I would worry very much about, right? We're very used to this, that we're always in some corner trying to simplify things. And yes, please.
Yes, so you mentioned that in certain circumstances, when you add disorder, you increase the conductance.
Yes.
And it's just a remark which probably needs to be think about that. So it's not a real question, or there are several questions that to be thought about. We have seen, for example, in quasi-crystals, okay, where the very peculiar arrangement which is ordered but not periodic. The experiment we had when we did in the group of Grenoble some calculation is that if you add disorder, okay, then you increase also the conductance. In the sense that the peculiar arrangement of atoms in the quasi-crystals localize the wave functions, and then when you add disorder, then you break this spatial arrangement, and then you delocalize, so you increase the condensate. So
yep. No, I mean, I would say this statement, adding disorder increases the conductance is a generic statement. In this particular case here, it's in a completely white noise potential, no special structure, it's only a consequence of this symplectic symmetry. It's only a concept of the symplectic symmetry and the absence of a quadratic term. Yes?
So would the result be the same if it was a scalar equation with the same thing?
No, certainly not. Certainly not. Well, I don't even know what to do with the scalar. You mean remove the sigma, but then it's no longer time. Then p2 minus p doesn't. You can't remove the sigma. If you remove the sigma, you have to do p squared. If you need sigma to be able to have this symmetry. Right? If you just have P, then you've broken. No, if you just have P, you've broken symplectic symmetry, and then it's over. No, this is what is called a symmetry class. So the symmetry class is very much constrained. When you tell me the symmetry, this is the Hamiltonian, that is it, and good. So this is the first thing. That's cool. So yes, you can break it. This is how actually I would typically break it. I would just add a sigma z term, a magnetization. You see? That's how you break the symplectic symmetry. You just add a perpendicular magnetic field or a perpendicular magnetization, which is couples to the spin in the z direction, but without a momentum. Without a momentum. And then you're localized. All states are localized. And in practice, this term here, and this goes back to the question of Denis, this term here actually also appears because typically topological insulators some material, I'm looking at the surface, it will typically be a thin film, there'll be a top surface, there'll be a bottom surface. Coupling between top and bottom surface effectively also is this term here. So here I say it, right? Single cone Dirac fermions is essential. You only need one species of Dirac fermions. If you have two species, then it's gone, and that's somehow and there are fundamental ways to think about that. Why two species localizes and one species does not localize, but this would really carry me a bit farther. Good. Yes. No. So, as I said, as recently as 2007, there was a debate whether this was the scaling diagram or the competing scaling diagram actually went down here. There's even a white dot here because my original graph had both of them. I removed one. You see the white dot here? So, smart people are working in this field for decades, think this might be a possibility. So, no, we don't have a theory for this. Not something which we do understand why it would be like this, and ultimately it's the numerics which somehow convinces you that this is what's happening, and yes, this is what you have to get used to. Basically, working in localization at all. There are very, very few things. If the disorder potential is weak, there are very, very few things which you can calculate with some level of rigor, and you'll have to rely on insight and numerics to somehow make it. But the good thing is that all of this is somehow qualitative, right? So it's either this or this. So this is something which you could distinguish in numerics, and then yes. Yes, please. Yes, the physical intuition which I have, but it's kind of like a bit more advanced, as you say that this Dirac cone has this notion of a Berry curvature, which is some topological thing. And if you would localize it, you would basically be gapping it out. You would lose the Berry curvature, which is not possible. And that's why you need, once you have two of them, then they have opposite Berry curvature, then they can just annihilate. And actually a manifestation which is simpler, but which is ultimately the same thing, is let's just look at this Dirac cone. Instead of having disorder, let's just add some perturbation which preserves the symplectic symmetry. Can I split this crossing point? The Dirac cone has this crossing point. Can I split it, making a gap? Just a simple toy calculation, not disorder. Just add anything to your Hamiltonian, and you very quickly will convince yourself that symplectic symmetry protects this crossing. In that context, it's known as Cramer's theorem. So this already shows that really this symplectic symmetry has some magic protection there, and. But yes, yes.
The next slide, when you claim the Dirac localization, is anything through relativity relevance? For this case, when you claim that there is, I won't give up on people being able to prove anything as per their localization, but when you claim there is localization, is anything true?
No. Okay.
How
No, if you ask me about mathematicians studying the problem of localization, I don't know anyone who has done anything else than the original Anderson problem, which is p squared over 2m Laplacian plus v. I mean, no one is. There's nothing. Literature is empty. All the mathematical rigorous stuff is p squared over 2m plus v, Laplacian plus v. All of this is just, first of all, because it's only 10 or 20 years old, mathematicians don't care, and yes. So now you actually no. Let me another question which you could ask about this thing is it in the same universality class as the quantum Hall effect? That is a question we do have an answer. First of all, so time Russell symmetry is broken. Symplectic symmetry is basically, so there's no time Russell symmetry here. And you could add, you could imagine, suppose I would add to, I would have like a, so you could ask, since time Russell symmetry is broken, is it in the same universality class as the quantum Hall effect? So will it have the same critical? No, because I've broken, yes, no. If I add a vector potential, I'm in business. If there's no doubt there. But here I'm breaking time Russell symmetry in a different way, by the same, basically what we physicists call the Zeeman effect. We're breaking time Russell symmetry not by adding P plus EA, but by saying I have something which couples to the spin. It's also breaking time Russell symmetry. So this is a question physicists have worked on, and the answer is no, it's a different universality class. It's a different universality class, different critical exponents. And in fact, this is one case where one critical exponent we can't calculate exactly. That's a critical exponent when the system delocalizes when average mass is 0. And that is one critical exponent which we know exactly. There's no... Both V and M, both V and M are weakly disordered. I only do weak disorder. Both V and M are weakly disordered. When the average of M is 0, it's still disordered, but the average of M is 0, then it delocalizes, and that's one critical exponent which we can calculate exactly. Yes? How the?
How the fermionicity has been playing a role in the whole calculation? Specific only for fermions and
fermions? No, there's okay. So no, this is not specific for fermions. It's all single particle physics. It's specific for some object which is described by a wave equation. It has a spin 1/2 degree of freedom. But you could, I mean, people could do this in cold atoms, people do this in optics. You could very well engineer your system so that it has a spin 1/2 degree of freedom, and then you're in business.
any symmetric term is specific for fermionic kind of treatment?
No, I never used the word fermions. I think I said massless fermions. No, I said fermions. Oh my goodness, I said Dirac fermions. Yes, we call them, I don't know, we call them Dirac fermions, but it's really a wave equation for a particle with an SU2 degree of freedom. And in fact, this is important because this is a big business in cold atoms. They would say simulate a fermion. That's the language which they would use. Simulate an emergent fermion in a cold atomic system. Because ultimately, if you look at this, you just say it's just something which has an SU2 degree of freedom. Could be some two-level system, whatever. Good. Yeah, we're doing great, friends. And because I have just one more thing, which is Majorana fermions. That's a bit more recent. I think Majoranas emerged 2012, 2010. Again, an obsession. Every single CONTMET archive will have probably 10%. I say 20% topology, 10% Majoranas. It's an obsession. So what is Majoranas? So what is the Hamiltonian? Well, it looks kind of similar. Just a moment. Here it is. Let's look at the Hamiltonian. So again, px sigma x plus py sigma y, that's our old friend. Now it does have a p squared term, but the p squared term is multiplied by sigma z. Before, I would just say p squared term is multiplied by scalar, by unit matrix. Now p squared term is multiplied by sigma z. Well, if you look at this and you're not a physicist, you say, oh my goodness, these physicists, they come up with the weirdest things. Now they do this, now they do that. Please go home, right? And you cannot calculate anything, which is true, right? Which is true. The reason why we're obsessed with this Hamiltonian is this describes a superconductor. This describes a superconductor. And superconductivity is kind of important. It describes a superconductor. Now, the sigma is not the spin. It describes a spinless super. Spin is gone. I use the same sigma because it's still a SU2 degree of freedom, but it's an SU2 degree of freedom of electrons and holes. So again, this is, if you're a condensed matter physicist, you're familiar with this. If you're not, you shouldn't care. It's just some, in superconductivity, we have electrons, positive, negatively charged particles. We have holes, positively charged particles. And they're coupled, because you see this is sigma x and sigma y can couple electrons to holes. It can scatter electrons into holes. And this thing here just says that the kinetic energy of an electron is minus the kinetic energy of a hole, right? Because it's multiplied by sigma z. And then there's still my old friend scalar potential. And scalar potential in this context is an electrical potential. Electrical potential acts with opposite sign on electrons and holes. That's why it has a sigma z. So this is electrical potential acting with opposite sign over electrons and holes. Kinetic energy acting with opposite sign over electrons and holes. And a term, this is called the pair potential, jargon. It's called the pair potential, which couples electrons to holes. This is a very important Hamiltonian. You might not say, I don't want to be bothered with this Hamiltonian. This is the Hamiltonian because the particles which obey this Hamiltonian are called Majorana fermions. They're not Dirac fermions. Dirac fermions was a different Hamiltonian. They're called Majorana fermions for some historical reason. Ettore Majorana, some Italian physicist, who knows, who cares. What's the symmetry? You know, that's how we, whenever I, you know, if we're in the business of studying localization, we have this notion of universality classes. So we have this notion, say, we don't really worry what the specific Hamiltonian is. I don't really care. I have to identify the symmetries. If I identify the symmetries, I know what the scaling diagram will be. I know that the critical exponents have some value which are universal in that symmetry class, so I'm done. So this is the first thing you do if you investigate a new problem. You say, let's look at the symmetries. Is there symplectic symmetry? Well, let's look. P to minus P, sigma to minus sigma. This one's okay, this one's okay, this one's not okay. This one's also not okay. No symplectic symmetry, gone. Is there any other symmetry? Well, yes, there is. You have to hunt for it a bit, but then you find it. There's this thing which is called charge conjugation symmetry, which is that if you take the complex conjugate and conjugate with sigma x, you get minus h. Complex conjugate here in the real space basis, so P is minus I ddx, right? So P also goes to minus P. And you could even check it. You say if I say P goes to minus P, okay, this changes sign. Sigma x doesn't change sign. This thing is real, right? Py times sigma y is real, because Py is I ddx and sigma y is I. So this thing's real, but if you conjugate with sigma x, it changes sign. So this one also changes sign. This one changes sign because of the sigma z. This one changes sign of the sigma z. It holds. So this thing has this thing which we call charge conjugation symmetry, particle hole symmetry. And it has one dramatic consequence, and that's why we call these particles Majorana. Let me explain this to you. So there is a basis transformation. It's just a unitary transformation. Sigma z goes to sigma y goes to sigma x goes to sigma z. A unitary transformation. If you do that unitary transformation, and this was only discovered 2015. It's crazy, but it was discovered very recently. If you do this unitary transformation, the Hamiltonian becomes purely imaginary. You say, shouldn't it be Hermitian? Yes, it's Hermitian. So if it's purely imaginary, it must be antisymmetric. It becomes purely imaginary times an antisymmetric matrix A. This is not the vector potential. This is just some antisymmetric operator, skew-symmetric operator. Now, if it's purely antisymmetric, how does the wave equation look like? The wave equation is I d psi dt is h times psi, right? So now you have I d psi dt is I times a times psi. Now you divide both sides of the equation by I, and you get a real wave equation. We've never been used to that in quantum mechanics. In quantum mechanics, we do not have real wave equations. All our wave equations are complex. Now we have a real wave equation. This has never been noticed or happened before, that we now have quantum particles which satisfy a real wave equation. So the wave function is real. Psi of r and t is real. It has no phase. You know, phase is supposed to be the important thing of quantum physics. Majorana fermions have no phase. And so this is absolutely crazy. When I didn't discover this, but I stumbled upon this like 10 years ago. 8 years ago, and it opened. So let me just tell you one of the things which I liked immensely. I'm not going to give a talk on this here, but I enjoyed this so much. We know about scattering theory, right? Scattering theory is all about phase shifts. You know, particle comes in. There's of course probability. Particle comes in, particles reflected, but then there's a phase shift. Now you have to develop a scattering theory without phase shifts. So what is the scattering matrix? Scattering matrix is a unitary matrix. Right? Why is it unitary? Well, it has to conserve particles. Oh no, I'm out of the camera. I have to be back here. Camera's here. Can't walk around. So scattering matrix is a unitary matrix because it has to conserve particles. And then it has these complex numbers in the unitary matrix give you the phase shifts. Now you have to develop a scattering theory for orthogonal matrices. Right? Orthogonal matrices still conserve particle number, but they have real elements. No one had ever developed a scattering theory for orthogonal matrices. It made no sense. It made no sense. And now it's not only it makes sense, this is what Majoranas do. Scattering theory for Majorana fermions is a scattering theory for orthogonal matrices. So it's this way, if I was transported back to 1920, you know, when quantum mechanics was still developing and young kids, I was kind of young in 1920, young kids could do all kinds of crazy things, harmonic oscillator, you know, all these fun things which you now give as an exercise, and then they could write a paper on it. I was transported back to 1920. I could do all kinds of elementary quantum things with scattering theory for without phase shifts. Okay, so that's the Majorana fermions. I'm doing really okay.
So,
Yes.
okay, maybe
No.
so, is there any localization?
Yeah, of course, that's not. No, this is the introduction. I introduced to you Majorana fermions. Now, of course, the question. Don't bother us with all this stuff. Tell us, do they localize or not? Here it comes. Here it comes. So time-rest symmetry is broken. There's no symplectic symmetry. Time-rest symmetry is broken. So you might say it's probably quantum Hall effect. It's probably quantum Hall effect. And you're almost correct, but not quite. Not quite. So what do we know about quantum Hall effect? In quantum Hall effect, we have edge modes. Okay, now call it Majorana edge modes, big deal. In quantum Hall effect, we have edge modes. And then we have localized states, bound states in the interior. Right? That's the transition, the phenomenology of the quantum Hall effect. In the interior, the states are bound, localized, and at the edges, we have the propagating states. Same thing here. Same thing here. Same thing here. These Majorana edge modes do not carry charge. Charge is not conserved here because of this electron and hole scattering. They carry heat. So the jargon here is this is the thermal quantum Hall effect. But big deal. Just whenever you say voltage, think of temperature. Whenever you see electrical current, think of heat current. The only miserable thing is that the unit of heat conductance, unit of electrical conductance is squared over h. It's memorable. The unit of heat conductance is miserable. I'm pretty sure no one here, just without Googling, will be able to tell me the unit of heat conductance. It's some miserable combination of fundamental constants. We'll get there perhaps in just a moment. But never mind. This looks very much like quantum Hall effect. Now comes the key difference with quantum Hall effect. Here it comes. In the quantum Hall effect, these bound states can be at basically any energy. Basically, if you would semi-classically calculate this bound state, you'd say it has to enclose. I mean, when I go around it, the phase has to be a multiple of 2 pi. Right? That's how you find. So if you would have like a mountain, this mountain will bind some states at some levels where the phase happens to be 2 pi. Majoranas have no phase. What does it mean? It means all these bound states are at 0 energy. Isn't this crazy? You could perhaps engineer a potential landscape, engineer a very special potential landscape where all the bound states are at 0 energy. And then there could be higher states, but let's say that you have a whole bunch of bound states at 0 energy, but it would be very special. Nobody would say, why would you do that? You don't have to engineer anything. Just give me some random potential landscape. All the bound, there will be higher bound states, but there will be also a set of bound states at 0 energy. If they're all at 0 energy, it means they will be able to tunnel resonantly from one state to the other. You don't have to fine-tune anything. And so there's the probability of metallic conduction, which is not possible in 2D. And indeed, that's what happens. So again, this is a computer simulation of the thermal conductivity. Again, lost my cursor. Okay, never mind. The thermal conductivity, okay, here it is. The thermal conductivity plotted on this axis and the system size on the other axis. And you see here the scaling of a metal. And here the scaling of an insulator. There's a metal insulator transition. And here you see the spike in the density of states at zero energy. That's these percolating states, bound states at zero energy. So there's a metal. The word is thermometal. It's called a thermometal. Let me show you the phase diagram. This is how the phase diagram looks like. So here we have disorder strength. Here you have Fermi energy, chemical potential. If the disorder is weak, these bound states exist, but they're somehow spatially separated. They could tunnel, but they're too far away. But then as you increase the disorder, the bound states come closer together, and you get percolation. And this percolation is resonant, because they're all at zero energy. Also in the quantum Hall effect, we talk about percolation, but there it's non-resonant. They're all different energies. Here they're all at the same energy, so they can tunnel resonantly to the system, and here we have a thermometal. Now, these are critical exponents, approximately 1, that's what we calculate numerically, approximately 2, that's what we calculate numerically, and thank goodness, 1 equals sign, friends. This is 1 critical exponent which we can calculate exactly. Nu is 1. So that's cool, right? Average chemical potential zero on this line. So if you approach this line, the localization length diverges with an exponent which is exactly 1. And here it's only numerics. Cool. Thermal metal. Never heard of this before. Majoranas do that. Yes, and they have the same logarithmic scaling, of conductance with sample size, length over Fermi wavelength or mean free path. This is the thermal metal. So this log L scaling here is characteristic of a thermal metal. I have an experiment. Let me show you the experiment. Yeah, I could show you the experiment. I still have a couple of minutes, 3 minutes actually to be precise. This is one, and then I'm done, so no worry here. No, I'm going to skip this because it would carry me. Let me just close now. So this is a summary of what I talked today. I gave you a whole bunch of new Anderson localization transitions, if you wish, or topological phase transitions, or quantum phase transitions. I mentioned symmetry classes. This is whether you have time Russell symmetry. This is the symplectic time Russell symmetry, spin rotation symmetry. There are topological quantum numbers. This is how we classify these things. And this is what we know about them. So there's some critical exponents. As you see, mostly we have approximate signs. There are 2 equal signs here. These 2 are known exactly. And the rest is not known. And so it's rich. It's very, very rich. There's lots of more stuff to do. It's pretty much all, intuition, understanding in general terms, and then do numerics to test that it's true. There's no real mathy theory, but that's something I got used to. Thank you. We have so many questions. We can quit for lunch, right? For coffee.
2 minutes for
Yes. The only critical exponent where lots of effort has been made to find it in experiments is the quantum Hall phase transition. Also because it's the oldest, right? People since 1918 have been trying to do that. And there's not quite a factor of 2, but certainly a 50% disagreement with the best numerics. And we have no idea what, it could be, in this business of condensed matter physics, if theory agrees with experiments, typically we say probably electron-electron interactions. But that's just something to hide behind. It just means let's push it in a corner. Let's push it in a corner where nobody can calculate it, so I'm safe. So there's a big discrepancy theory in experiments. There's actually some recent work by one of my students, Elizabeth Dresselhaus, who tries to somehow reconcile this. She has 2 PRLs which somehow actually argue against single parameter scaling and argue that there is some non-universal effects there. So there's work to be done there. This is the only one. I don't know of any other experiments, also not in cold atoms or optics, on calculating other critical exponents. And then I'll have to remember that. I'm not sure that I'll be able to do that. No, but you were great. You asked many questions. I like that. Please. Yes. So if they're exactly at zero energy, obviously they will not carry heat. So you'll have to heat them up and give them some finite energy. No, that's absolutely. So in equilibrium, which is when they're all zero energy, they won't carry heat. So you have to give them some energy. It's basically this edge mode. It's the edge mode which will be conducting heat. The edge mode is just some dispersive mode. It exists. The bound states are zero energy, right? Bound states are zero energy and not conduct anything. But the edge modes, they have some continuum of energy, so you just inject it at some non-zero energy.